Hi all, I welcome you all to the next lecture today. Here Professor Ravi Kumar, School of Mechanical Engineering, Sastha deemed to be University, Tanjavur. In previous lecture, you have covered the derivation for the internal energy enthalpy changes, right, using the Maxwell relationship. Also, TDS relation was expressed into three different forms, right, in terms of coefficient of expansivity and coefficient of isothermal compressibility. Today, we are going to see the remaining topics of thermodynamic relations. Particularly, we will be focusing on Joule Thomson coefficient. Then we'll go for Clausius Clapeyron equation, and the final topic will be the Gibbs phase rule. All right, so let's start our discussion for today. The first topic is Joule Kelvin effect. So Joule and Kelvin, they together basically conducted a experiment, and they finally related the property variations to derive a coefficient that is called Joule Kelvin coefficient. So the experimental setup was something like this, right? The insulated container, right? In that, this is very small passage through which fluid was forced to go through, and finally it was expanding here. So pressure upstream and downstream, pressure temperature upstream and downstream are measured with the help of suitable manometers and thermometers attached at upstream and downstream locations of the flow. Alright, so basically whenever we are setting the flow to go all of sudden compression and then followed by the expansion. You look at all of sudden compression followed by the expansions of fluid. Particles do not have too much time to basically going too much change in properties. Even though there will be a appreciable change in pressure, right? Pressure, but overall there will be no change in temperature. So if you look at the temperature variation, there will be almost very negligible change in temperature will be found, or you can say this kind of process is known as throttling process. So during throttling, enthalpy remains constant. So enthalpy before throttling and after the throttling will have some value, but there will be a significant change in pressure. So by keeping the initial pressure temperature constant and with the help of this valve, right, one valve is attached here, with the help of valve, the flow can be throttled to any condition, right, any point condition, and every state, right, by which flow is getting throttled will be an equilibrium state. So that can be easily represented over the property diagram. So look at here, when initial pressure and temperature is fixed, and we with the help of valve we are throttling it to different pressure and temperature. So we will getting these kind of points where pressure and temperature will be entirely different than the initial pressure and temperature. So that's our initial pressure temperature. Initially you have fixed some value, then again next time you further increase the value of pressure and temperature at initial, then you uh, fix the quantity at that point and then operate the valve, you will get the second curve. So like that you can get the n number of curves here. These all curves are nothing but the isenthalpic curve, or you can say the lines of constant enthalpy. Alright. So, as I mentioned, a gas is undergo continuous throttling, right, via valve. The valve is there, right? So, initial pressure and temperature for a given initial pressure and temperature, it can be throttled to any condition, right? Any condition. So, all these points what you are getting, right, will be equilibrium point, and you can draw a line along passing through this point, and this line is known as the constant enthalpy line. Constant enthalpy line. So if you look at this curve, right, if I increase the initial temperature, right, if I increase the initial temperature is higher, in that case this curve will be almost flat. That means it will become approximately means exactly constant enthalpy line initially, but these lines are approximately constant enthalpy lines, right? So if I increase the initial temperature higher side, these curves will become flat. So if you look at the slope, if slope you are measuring this side slope, right, you are getting negative slope. If you are measuring this side, you will get the positive slope. So negative slope means if you are going towards left side, right, from right side to the left side, that will represent the heating process. If you are going this side, right, from starting from this maximum position, if you are going downside, but slope is positive. If you are going downside, that will be showing the cooling, right? That will represent the cooling, and this is called heating. Look at this. This is the temperature ordinate. If you are going like this, it is heating. If you are going like this, cooling. And there is a point which is called maximum enthalpy point, right? Maximum enthalpy point is for all the curves. You will be getting the maximum enthalpy point. If you draw a line through the maximum enthalpy point, that is called inversion curve. Inversion curve. That is the location of maximum enthalpy. And if you are going to the right side of the maximum enthalpy, that will show the heating process. If you are going to the left side, it is called cooling process. Right. So the curve passing through all these points is called isenthalpic curve. And if we change the initial pressure and temperature, you can get another curve. So like that, you can get a number of curves. As I clearly mentioned, a curve passing through the maxima of these isenthalpic is called inversion curve. So look at this. So at different pressure and initial pressure and temperature, you got different kind of isenthalpic curve over the temperature pressure ordinate. So this is the maximum position, right, for all this. For this is the max position is this vertex. This vertex similarly for this vertex. If you draw a curve passing through the maximum enthalpy point, right, that is called basically inversion curve, and this is the maximum inversion temperature. This is the minimum inversion temperature. Minimum inversion temperature. So in a detailed view, look at it will be something like this, right? This is the basically inversion curve, and these all are isenthalpic curve. If you draw this slope here, it is slope will be negative, and this side it will be slope will be positive. Slope will be positive. Keep in mind. At the lowest value, lowest point inversion temperature, inversion slope will be 0, right? So slope, if you find out the slope of temperature and pressure ordinate, that will give the Joule Kelvin coefficient. So Joule Kelvin coefficient is defined as the change in temperature per unit of change in pressure when enthalpy is constant. So along any enthalpy curve, whatever slope you are measuring, that is called Joule Kelvin coefficient. Clear? So as I clearly mentioned, so at this point where slope is basically negative, right? Slope is negative. If you are going towards the point B, that will represent the heating process. At this point, if slope is positive, if you are going from C to D, that will be representing the cooling process, right? That's the basic idea. So by changing the pressure and temperature, you can change the conditions of heating and cooling. So as this point is clearly covered. So as a higher initial starting temperature, isenthalpic curve will become flattened and more closely horizontal. And in the case of ideal gas, it will be a horizontal curve, right? Throttling process will have no losses, or no losses involved. You will get a constant horizontal line for throttling process, right? Similarly, there will be a maximum inversion temperature, and whose value will depend on the type of gas. And for cooling to occur, initial temperature must be less, right, than the maximum inversion temperature. For such, T is optimum. Initial pressure is on inversion curve. So you can look at here. If you want a cooling right to happen, then maximum inversion temperature you will find here, right, at the top. It should be lower than this. So now we'll derive the expression for the Joule Kelvin coefficient, right, in terms of fundamental properties. So mu may be expressed in terms of Cp PVT as follows. From property relation, TdS is equal to dH minus VdP, right? So from there you can write dH is equal to TdS plus VdP. So from the TdS relationship, recently we derived for open system, we can write TdS is equal to Cp dt minus T and dou V by dou T at P into dP. This equation we got from TdS relation. And in previous lecture, we derived the expression for change in enthalpy, right, which is nothing but dH equal to Cp dt and bracket term T dou V by dou T P minus P dP. Clear? So this is dH. But for throttling process, we know that there is no change in enthalpy, so we can put this equal to 0, right? This dH is equal to 0, and we can find out the expression for Joule Kelvin coefficient. So for constant enthalpy, dH is equal to 0, we can substitute this is equal to this exactly equal to 0, and in place of this term, right, T dou V by dou T at P, we can substitute this value, right, using this expression. Right, so you can substitute that, or if you don't want to substitute, then just you solve this, right? Just you solve this, and at the end we can substitute the value. So just look at here. So we are writing first term Cp dt at h plus bracket. We are taking minus sign of it out of it, this bracket. So this become plus here, and this as it is into dp, and enthalpy constant, right? That's why this term is coming enthalpy constant. So further you can take Cp dt that side, and the same term which we are getting here is here. So Joule Kelvin coefficient is defined as dou T by dou P at H, right? So dou T is already available, so we can divide this entire equation by dP, right? And we can get the Joule Kelvin coefficient. So mu is equal to dou T by dou P. If you do this, dou P will go out. So whatever term is there divided by Cp is nothing but Joule Kelvin coefficient. This is here. So for an ideal gas, right, we need basically dou V by dou T P value and other parameters as it is. So for an ideal gas, we know that ideal gas equation of state P V is equal to RT. So specific volume can be written as RT by P. And what we basically need, we need to differentiate specific volume with respect to temperature by keeping pressure constant. So if you do this, you can get simply R divided by P, right? R divided by P square. So R divided by P. So R divided by P you got, because you are differentiating with respect to T. So R divided by P. So R divided by P is nothing but V divided by T. In other way we can say, so you got R divided by P, that is nothing but V divided by T. Substitute the value of dou V by dou T P in the equation of mu. So I am having mu here. So here I need to put the value of dou V by dou T at P, that is coming as V divided by T. If you substitute the value, that you will get mu is equal to 0. That means what? For an ideal gas, you know, temperature will not change. So temperature is not going to change. There will be no change in Joule Kelvin coefficient. So Joule Kelvin coefficient will be 0 in that case. So therefore, for an ideal gas throttling, there will be no change in any temperature, right? That's why we say for ideal gas, enthalpy curve that you are getting will be a straight line. Now let enthalpy is a function of pressure and temperature. We can write change in enthalpy, right? Dou H by dou P T dP plus dou H by dou T P dt. Now for constant pressure process, we know that the heat transfer is equal to change in enthalpy, right? Or you can say dH is equal to Cp dt, right? Cp dt. So we can write dH by dt is equal to Cp. So we are getting dH by dt here. So this term is representing basically Cp. So you can substitute here value as Cp. So we can write dH by dt is equal to Cp. So we can write dH is equal to this term plus Cp dt. Clear or not? Now for constant enthalpy, right, we can substitute this equal to 0, and we will try to solve this to get the Joule Kelvin coefficient. So for throttling process, dH is equal to 0. So we got this term plus Cp is equal to 0. So Cp from here can be calculated. Cp is equal to these two terms negative. Look at this term dou H by dou P. This we can directly get from the curve, right? And what is this term? This term is your Joule Kelvin coefficient, dou P by dou T at H, right? Dou T by dou P H is basically my Joule Kelvin coefficient. So this is the inversely proportional of the Joule Kelvin coefficient. So I expressed here Cp is equal to minus 1 divided by mu dou H by dou P at T, where dou H by dou P at T is known as constant temperature coefficient. Constant temperature coefficient. So like that you can derive expression for Joule Kelvin coefficient, right? It has been derived for the what we say throttling process. So they carried out n number of throttling processes, they draw it, and finally they concluded that the slope of the temperature and pressure ordinate for throttling process will give give us the Joule Kelvin coefficient. Next topic is Clausius Clapeyron equation. So Clausius Clapeyron equation basically gives the relationship between saturation pressure, saturation temperature, specific volume, and enthalpy of evaporation for two-phase zone particularly. So we can say Clausius Clapeyron equation is a relationship between the saturation pressure, temperature, enthalpy of evaporation, and the specific volume of two phase involved. So with the help of Clausius Clapeyron equation, one can easily determine the properties variation in two phase zone. Alright. So this is basically my pressure and temperature curve, right? And these are the different processes. So this is a solid zone, right? And this is called triple point. So triple point is the temperature at which all the three phases coexist in equilibrium, right? Coexist in equilibrium. And if you are directly going from solid to vapor, that is called sublimation curve. This curve is called sublimation curve. Directly from solid to vapor you are going, alright. And if you are going from solid to liquid, that is called fusion curve. If you are going from liquid to vapor, that is called vaporization curve. As clearly mentioned from properties of pure substances that there will be a triple point line, and below triple point line liquid phase will not exist. Liquid phase will be existing only above the triple point line. So below triple point of line, if you are at solid side, if you want to change some temperature, you will directly go to the vapor zone. So there will be direct conversion of solid to vapor. Below triple point line. So if you are changing this, you directly go to the vapor. See, this zone is completely vapor. So the intermediate phase change, right, line between this line is phase change process, it will call sublimation. And if you are going from solid to liquid, there is a fusion. And if you are going from liquid to vapor, that is called vaporization. All these three curves will meet at a single point, that is called triple point. Triple point is a temperature at which all the three phases coexist in equilibrium. And also we have seen that for some pure substance, this fusion curve slope will be positive or negative, right? Like for water which contracts on freezing, right? Especially in that case, what will happen? Slope will be negative. So fusion slope will be negative for the water, and for other pure substances will be positive. If you look at the evaporation curve and the sublimation curve, these curve slope will always be positive. So Clausius Clapeyron equation can be derived in different ways. One can derive, but here I am giving you a simplest, derivation by using the concept of Maxwell relation that already be derived. So from Maxwell relation, dou P by dou T at constant volume is equal to change in entropy divided by dou V at temperature. This we know from the Maxwell relation. So let us consider change of state from saturated liquid to saturated vapor of a pure substance which takes place at constant temperature. During the evaporation, the pressure and temperature are independent of the volume. This is one of the fundamental peculiarity of phase change process, right? And we are considering the case of conversion of saturated liquid to the saturated vapor. So we can say dou P by dou T is nothing but a change in entropy between the gas and liquid. So Sg minus Sf divided by Vg minus Vf. If you look at this term basically, where this is specific entropy of saturated vapor and this is the specific entropy of saturated liquid. Similarly, this is specific volume of the saturated vapor and this is called saturated liquid specific volume. So in other way we can say this is SFG, this is called V suffix Fg. Clear or not? So everything is there, specific entropy of saturated vapor, saturated liquid. But we know that SFG, when you are going to find out the entropy change for a phase change evaporation process, is nothing but enthalpy of evaporation divided by T, because this process occurs at constant temperature. So entropy change what you are calculating would be calculating based on constant temperature process. So Sg minus SFG, that is nothing but HFG divided by T, and Vg minus Vf is Vfg. So we can substitute this value back in that equation, this equation, to get dou P by dou T. So if you substitute, you can get dP by dt is equal to SFG divided by VFG. right? VFG and SFG is what? HFG by T, you can substitute. This is known as Clausius Clapeyron equation for a phase change process from liquid, saturated liquid to the saturated vapor, or you can say it's a Clausius Clapeyron equation for vaporization process. Clear? Or evaporation process. So here dP by dt is the slope of vapor pressure versus temperature curve, and knowing this slope, right, and the specific volume from experimental data, one can easily find out the enthalpy of evaporation, can easily be calculated, which is very difficult to calculate analytically, means very difficult. But from experimental data, already we know the specific volume, and this slope can be taken from the experimental data curve between pressure and temperature. Easily one can find out the HFG. Next, at low pressure, at very low pressure, there will be no difference between specific volume of saturated vapor or mixture. So we can say Vg is equal to exactly Vfg. So dP by dt is equal to HFG by TVg, right? So now using the equation Pv is equal to RT, just put V is equal to RT by P in place of Vg. So the same equation can be reconverted into HFG into P divided by RT square, or you can directly find out the HFG. HFG is equal to RT square divided by P and dou P by T, and this is the slope. So above equation may also be used, right, to find out the enthalpy of evaporation. So if you further rearrange this term, right, these terms again, you can write dP by P. Take these two terms together and rest of the term another side. So dP by P is equal to HFG by R into dt by T square. Why I am doing this arrangement? I am doing this arrangement to find out the final pressure and temperature by considering the initial pressure and temperature. So if I integrate this term, I can easily relate between two pressure and two temperatures. So the above equation can be integrated, right? If you integrate this, you can get this relation. Ln P2 by P1 is equal to HFG by R, 1 by T1 minus 1 by T2. So using this equation, right, if I know initial pressure and temperature, final pressure and temperature can be calculated. So knowing initial pressure and temperature, one can easily find out the P2 and T2. So from Clausius Clapeyron equation, we see that slope of vapor curve is always positive, because specific volume of saturated vapor will always be greater than the specific volume of liquid, and also HFG is always positive. Consequently, vapor pressure of any simple compressible substance increasing with temperature. It can also be shown that the slope of sublimation curve is also positive for any pure substance. But the slope of the melting curve may be positive or negative, right? In the case of water, especially, it will be negative, which contracts on freezing. So this is basically regarding the Clausius Clapeyron equation. So from this, these three important outcome you can write about the phase change process, right, using the Clausius Clapeyron equation. Next one is Gibbs phase rule, and the Gibbs phase rule is basically being used to find out the number of independent variables required to specify the state of a pure substance. So if you want to know how many independent properties are needed to define the state of any pure substance, you need to use the Gibbs phase rule. So as per the Gibbs phase rule, this is the formula. Number of independent properties is equal to C minus P plus 2, where F is known as number of degrees of freedom, or you can say the number of properties required, and C is called number of components, whether it's a single component or it's a two component system, alright, and this P is known as number of phases and plus 2. So take one example, let's suppose it's a nitrogen. Nitrogen, we can say C is equal to 1, because nitrogen is a single component and phase is also 1. So we substitute the value, we can get F is equal to 2. That means what? To define the state of a nitrogen gas in a cylinder, two independent properties are adequate. If you take the case of closed vessel containing water and steam, water and steam are basically a single component but two phases. So phases are 2 and component is 1. If we substitute this value in this equation, we get the number of properties only 1. So one property will be sufficient to define the state. That's why for two phase zone, right? A mixture zone, either pressure is known or the temperature is known, we can find out the remaining properties. In your steam table also you might have seen that for the two-phase zone, if you know just pressure, we can use the pressure table and we can find out the remaining properties, or if I know the temperature alone, I can find out the remaining properties. If you take the third condition, a vessel containing water, ice and steam, that means there are three phases, but component is one, right? There are byproduct of water, so component is one, phases P is 3. If you substitute this value in this equation, you will get number of properties is equal to 0. That means you don't need any property, right, independent property to find out the state. But what then we will have to use, there is a point called triple point. So triple point is the temperature at which all these three phases comes into equilibrium. So triple point temperature enough is sufficient to define the state of the three phase zone of water, ice and steam. So using this very fundamental thing, right, you can find out the number of independent variables required for getting the state of any pure substance. So with this we are closing the today's discussion, and this was the last topic of thermodynamic relations, right? With this your first topic of your fourth unit is over, thermodynamic relations. So as a summary, what we have derived so far in 3 lectures, we started with general concept of partial differential equation, then we derived fundamental TDS relation, one TDS relation for closed system, another TDS relation for open system. Then we gone for deriving expression for difference in specific heat capacity Cp minus Cv in terms of the fundamental properties, pressure, volume, temperature, and also we have expressed Cp and Cv in terms of coefficient of expansivity and coefficient of isothermal compressibility. Later on, we derive expression for TDS equation in 3 different forms in terms of Cp and Cv, Cp separately and then Cv separately, then in terms of Cp, Cv combined in single form using both the TDS equation together, and in terms of coefficient of expansivity and coefficient of isothermal compressibility. Then we derive expression for internal energy, we derive expression for change in enthalpy as well, right? And finally, in today's lecture, we have seen a detailed explanation of Joule Kelvin coefficient, and we derived the expression for the same, and also we derived the expression for Clausius Clapeyron equation, which is very important equation by which you can clearly predict the behavioral change of properties in two-phase zone. Alright, here we have seen the 3 different cases, right? First case we have seen conversion of saturated liquid into saturated vapor, where we find out the enthalpy of evaporation. Second case we have seen the conversion of solid directly into the vapor, that is known as sublimation process, and also we have seen the case of triple point temperature at which all the 3 phases are coexist in equilibrium. So from the Clausius Clapeyron equation outcome, one can easily say that slope of vaporization curve will always be positive because the saturated specific volume of vapor will be greater than the specific volume of saturated liquid, and enthalpy of evaporation will always be positive. One can also prove that the slope of sublimation curve is also positive for any pure substance. If we look at the slope of the fusion curve, where phase change process is taking place from solid to liquid, right? That line, the intermediate line of phase change process is known as the fusion curve. Fusion curve may be positive or negative for the pure substance. It will be negative only for the water, because water is having a peculiar properties that when it is getting freeze, right, its volume contracts, right, and for remaining pure substance basically they expands. So in the case of pure substance whose volume is getting expanded in freezing, alright, your fusion curve slope will be positive, and for what in the case of water it will be negative. Then finally we have derived expression for the Gibbs phase rule, and Gibbs phase rule is an important discovery by which one can easily find out how many independent properties are needed to define the state of any pure substance, right. So by knowing the number of components, by knowing the number of phases, one can easily find out how many independent properties are needed to exactly put the state of that pure substance on property diagram. Once you know the state of pure substance, you can find out the remaining unknown properties, or you can exactly predict the behavior of that pure substance in a given domain. So these were the topics, right, or under the thermodynamic relationship. With this, I am closing this topic. In next class, when we will meet, we will start the last topic of the fourth unit, that is called Introduction to the Power Cycle and Refrigeration Cycle. So if you are having any doubt in the current content, feel free to write in the comment section, or you can directly approach to me on my WhatsApp number already I shared with you. See you all in the next class. Have a nice day. Good day.